So all of you are probably wondering why I have a giant periodic table and a bunch of numbers in there. Today we're going to be talking about electronegativity, and this is just a chart for all of the elements and their electronegativities. Well, almost all of the elements actually. Electronegativity, by definition, is just how much an element wants to hog out the electrons in the bonds to itself. These numbers represent the electronegativity, and it's called the Pauling scale. It's developed by a man named Linus Pauling, and it measures electronegativity by number. So, as the numbers get smaller and smaller, the less electronegative they become, and the bigger numbers represent higher electronegativity. So, if you look here, you'll see that elements like fluorine, oxygen, or chlorine are highly electronegative. Meanwhile, the elements over here on the other side, cesium, francium, and radium, are all rather electropositive, as we might call it. But as you all see, I have this word called diagonal trend here. Why is that? Well, it's because of many reasons. For one, there is actually a diagonal trend here. Why is it diagonal though? Well, it's because of the combined forces of an upward trend and a sideways trend. Elements tend to get more electronegative as you move up the periodic table because the outer shells get closer and closer to the nucleus. This means that the nucleus can exert more force on the nearby electrons, even if you're a valence electron. In other words, the valence electron shell gets closer to the nucleus, and the nucleus can pull on it stronger. So it makes the excess electrons easier to catch for the nucleus. Now there's also another electronegativity trend that occurs when you go sideways. The reason is that, although I didn't depict it here, there are still the noble gases: helium, neon, argon, krypton, xenon, and radon. As you can see, these guys are very close to the noble gases. So they're going to want to get electrons since it's like the fastest way to get to the noble gas configuration. These guys have 7 valence electrons, noble gases have 8 valence electrons, so it's just logical to try and hog electrons. It's just logical. These guys, on the other hand, are not really that much because they prefer to lose electrons because it's faster. They have like 1 or 2 valence electrons. So you may as well get rid of that entire shell and take care of the 8 valence electrons on the next inner shell. However, because this one's pointing up and this one's pointing sideways, the two forces combine each other and they go diagonal, making it the diagonal trend. But here's something interesting. Sometimes the trend is broken, like say iridium. Osmium is 1.5, so you may have guessed that the iridium should be more electronegative, right? But it's actually more electronegative than platinum or gold. The reason is that once you get into transition metals, things just kind of get awkward, and there are more breaking rules and stuff like that. So let's move on to bond polarity. Bond polarity is just how polar a bond is, just as its name states. Because if there's a more electronegative element and a less electronegative element, then you will depict their charges by a delta plus or a delta minus. Delta, a Greek letter of the alphabet, is used for depicting partial charge. This is called partial charge because it's not really an ion or anything like that. It's just because more of the electrons shift towards one of the elements. For example, here I have hydrochloric acid, also known as hydrogen chloride in some places. Hydrogen is much less electronegative than chlorine, right? If you go back to our chart here, you'll see that chlorine is 2.9, hydrogen is a mere 2.1. So this just makes sense that chlorine will hog the electrons a little more. So chlorine gets this delta minus, which depicts partial negative charge since more electrons are approaching the chlorine. Meanwhile, hydrogen gets delta plus charge, which depicts partial positive because the electrons are going away from the hydrogen. To find bond polarity, we have a very simple formula that even elementary schoolers can do. It's called the bond polarity, delta En, is basically the larger electronegativity minus the smaller electronegativity. I know, even a preschooler can do subtraction. Okay, but maybe not a preschooler, but still, if you can do subtractions, finding bond polarity is easy peasy. As the En, or bond polarity, gets larger and larger, the bond polarity also increases, so the bond becomes more and more polar. However, if En equals 0, then it is non-polar, so it doesn't have any poles, no delta plus or delta minus whatsoever. Now here's a little extra info for those of you who are wondering. If En is greater than, not greater than or equal to, greater than 1.7, the bond is considered ionic. If En is equal to 1.7, then it's considered to be half ionic and half covalent. It sounds kind of awkward that something can be half and half at the same time, but they actually do consider 1.7 to be the boundary between polar, covalent, and ionic. And if En is between 0 and 1.7, then you call it something called polar covalent. In other words, it's the same thing, delta plus and delta minus. And if En equals 0, as I mentioned, is non-polar covalent. So what's the difference between all of these? Now, ionic has a clear definition of plus and minus. For example, in sodium chloride, it's very obvious that sodium is plus and chloride is minus. But once you get to polar covalent bond, like hydrogen chloride as earlier, because the other nonmetal also has a tendency to hog electrons, it becomes more of a delta plus delta minus situation. And for non-polar covalent bonds, there's no such thing called charge. The electrons don't go anywhere. Because for here, carbon to carbon, both of them have the same electronegativity, so the electrons really are technically staying in the middle, and they're not going to go toward either atom. So it makes the molecule, or rather the bond itself, lack any charge. Now let's talk about something called dipole moment. Dipole moment has a very simple formula, which is basically a difference in charge, Q, times the distance between the nuclei, R. So if there are two atoms, like again, hydrogen chloride for example, here's the nuclei of each atom, the dipole moment would be the difference in charge times the distance between both of these nuclei. It's kind of logical that it's R because it's the radius of the hydrogen atom and the radius of the chlorine atom. Let me depict this. Now we have two major units for dipole moment. It's called either device or coulometers. Coulometers is a very large unit, and because of that, 1 debye is equal to 3.34 times 10 to the negative 34th power coulometers. Just for fun, let's try and convert this equation into coulometers into x debye. Well, let's do that. Since we want to isolate the coulometer term, we're going to divide the whole thing by 3.34. So once you do that, you get coulometers is equal to 1 divided by 3.34 times 10 to the negative 34th power, or debye's, right? But here's the catch. Because you have a negative exponent in the denominator, you would actually rise up to become a positive exponent. So this 10 to the negative 34th power will come up, and it will become 10 to the 34th power divided by 3.34 debye's. Now given that 3.33 is 1/3 reciprocal, no, 3.33 is 100 times 1/3, we get that it is about 10 to the 36th power over 3. 36th power divided by 3. Now this is just an approximation for the number of debye's in a coulometer. don't use this formula, just stick with 1 Debye is equal to 10 to the 34th power times 3.34 coulombs. Now just as a final note, dipole moment is treated as a vector quantity. For those of you who don't know what a vector is basically a line with magnitude, in other words, length or strength, and direction. Let me show you a few examples before you leave. So here I have the very classic molecule, water. I know, water. The thing we drink every day, yes. So if you look closely at water, you have 2 hydrogens and 1 oxygen. Everybody knows that, right? But if you analyze it even more closely, and based on the info you learned just a few minutes ago, you'll get that hydrogens will have the delta plus charge, oxygen has a delta minus charge. And because the hydrogens are going downward like this, and the oxygen is facing this way, because of that, the positive pole will go this way, and the negative pole will go this way. But here's the interesting thing, is that sometimes dipole moments can cancel each other out, right? Because they're vectors after all, and if you add vectors, sometimes they can cancel each other out. For instance, let's look at the structure of chloroform. Chloroform, also going by the name of trichloromethane, is a chemical compound that can be produced by reacting acetone and bleach. There are tons of videos about it. So if you look at chloroform closely, you guys are probably going to instantly know that chlorine will have delta minus. And it's pretty easy to know once you understand it, because chlorine is 2.9, carbon's electronegativity is 2.5, chlorine is definitely the delta minus. So hydrogen will logically be the delta plus, right? 2.1 to 2.5, carbon is more electronegative. So if you look here, the electrons are coming from hydrogen to carbon, so this way, and carbon to the chlorines, this way. So if you combine all of those vectors, you have a strong negative dipole facing this way. The thing that's funny about chloroform is that it's considered nonpolar, which I don't really understand. But still, the dipole itself is facing downward and is strongly negative. But check this molecule out. This one looks very similar to our last example, chloroform, except because we have 4 chlorines instead of 3, we call it carbon tetrachloride, or carbon tet for short. Now here, you may have again noticed chlorines are delta minus, and because you don't have any hydrogens on that chloroform, carbon will be the delta plus. But here's the thing, although it looks like it's just pointing this way, and this way, if you look at it in 3D, I'm actually drawing a tetrahedron. For those of you who don't know what a tetrahedron is, it looks something like this. Let me just draw it. Kind of like that. So in the center right here is the carbon atom, and in the center it's pointing towards all the chlorine atoms. But because the dipole moment is a vector, there will be one upward dipole here, sideways dipole here, here, and here. But because all of them are facing in different directions, all away from each other, they're actually going to cancel each other out, like that and that. And carbon tetrachloride has really no dipole at all. So that was a lesson about electronegativity, bond polarity, and dipole moment. Thank you for watching, and see you in our next AP Chemistry series. Bye!